We go over work, power, and energy now. So the first thing to understand is what work is. Now, work, of course, in a human perspective, the way we take work is not the way we're going to define it in physics. So we're going to define work as the product of the displacement. So that is product of displacement. And the component of the force. So that is component if you can't see properly. So component of the force in the direction of the displacement. So this definition is so much important for us to really understand, because when we just miss this, then we'll not be able to do anything much proper. So we are saying the only way we can have work is if we have got a displacement and also a component of the force. We are talking of component because at times force can come in two components. So assuming you've got an object which is here, and then you are pushing it at a certain force F, and then it moves it covers a certain displacement S, and then it reaches at this point there. Notice that this thing is, for it to move from point A to point B, it means that's moved forward. So the direction of displacement is in that direction, is going forward. And then notice that the force is also going forward. So the only way we can have work is when the force applied is in the same direction as the displacement covered. And so the formula becomes work is given by force times displacement. These two are in the same direction. Alright. Now, assuming there's a friction force, let's say there's kinetic friction, because whenever something is moving, kinetic friction always wants to oppose motion. So let's say there's kinetic friction there. Now, notice that kinetic friction is always goes in the opposite direction to the direction of motion. So the displacement is forward. The kinetic friction is in the back direction. That means work done by friction is always negative. So it will be negative this same kinetic friction and then multiplied by the displacement covered. Okay, so that becomes the formula for work done by friction. Now all this comes from the general form. Work is given by force times displacement and then cosine theta. So if you consider the first instance where you've got a force and displacement, force is going in that direction, and then notice that even the object moves from point A to point B. That means the direction of displacement is also like that. That's the displacement. So they are going in the same direction. Whenever things are going in the same direction, the angle theta is 0, and so this will be cos 0, and cos 0 is 1. So this portion is going to give us a 1. And 1 times Fs, that's why we find that the formula is just work is equal to Fs. But considering friction, friction is going in this direction. And then the direction of displacement is in the other direction. So notice that they are going in opposite directions. So if you connect these lines, displacement is like that, and then friction is like that. So this is making an angle of 180 degrees. And cos 180 degrees is a negative 1. That is why we see here it will be negative 1. Negative 1 multiplied by this, it gives us negative Fs, which is this formula then. So it all comes from just this very important formula for work. Alright, we need to get to understand much more when we are talking about work. Let's consider another case. What if you've been given, you have got of course an object which is here, and then you've got an applied force at a certain angle. Let's say the angle is alpha. So this is the force F, and then this object moves and reaches this point. So let's say this is the displacement S. Now what is the work done by this force then? So the work done by the force F is going to be equal to, we need to take the component of this force that is in the same direction as the displacement. So work is a product of displacement and the component of the force in the direction of the displacement. Notice that this force is going to be broken into this component, that is the y component, and then it is going to also be broken into the x component. So the x component is a component which is in the direction that is of the displacement. So therefore the work done by the force will be x component of the force multiplied by the displacement, and then cosine the angle theta. Now this angle theta is the angle between the component of the force and also the displacement. Now notice that fx is going in that direction, and then the displacement for the object to move from this point to this point is also going in the forward direction. So the angle between these two, if they are going in the same direction, the angle is 0. So this portion will be cos 0, which is a 1. And so it just remains that force, work done by the force will be Fx times S. Now Fx is given by, how do we find the x component? Now notice that for the x component we have got the angle theta here. If this is the x component here, that means it is parallel to this portion, so those two are equal. And as we can consider, this angle, this side is adjacent. So when it is adjacent, the trig ratio we are going to use is cos. So x component will be given by the applied force times cos the angle is alpha, and then times the displacement. Then that becomes the formula that we are going to use to calculate the work done in this case. What if you've been given a case where you are lifting something, you are going forward? Imagine you are here. You've lifted the bar. Let's say you are lifting something from the ground, and then yourself you are going forward. So notice that the force is working from down, like you used force to lift something from the floor up to the top, but you are doing work, but you are moving forward. That means the displacement is going forward. So work is going to be given by still force times displacement and then cosine theta. Now notice that the force is going up, but yourself you are moving forward. So the angle there is 90, and cos 90 is 0. So whenever you are lifting something, in physics you are not doing any work when you are going forward. So when you are lifting something, if you get tired, getting tired is due to your muscles and not because you are doing work. So you are not doing any work. The work is 0. So work should always be, the applied force should be in the same direction as the displacement in which you are going. Very important for us to understand. Alright. Now let's consider work due to position. What if the work due to, let's say work due to gravity. If you are on, let's say you have got an object which is here. We know that when an object is on top there, it is able to drop. So at the top there, it has got potential energy, and when it starts dropping, the potential energy is getting converted into kinetic energy. So the work done when an object drops from that point to the down is the same work when an object moves from the down point to the up, and that is given by the potential energy. And so work is going to be mgh. This is called work done against gravity. So that is the same as just potential energy. Now work done, what you need to understand generally about work is a scalar quantity and not a vector. It really doesn't depend on your initial and your final position, but just, it doesn't depend on the length of which you've taken to move, but it depends from your initial and your final, as long as you've reached your final. So what we are saying is this: take for example, you have got stairs, Whether you move from this point, you reach to the top using the stairs, or you move from the down, you use an elevator. It lifts you up to the up. The work done is going to be the same. And because you are going up, the work which will be done will just be mgh. The work doesn't depend on how far you have gone this direction. It only depends with how high you went. It just depends on the height. So we don't care about how far this place is. Whether one person can move just like we can see here. So we can see that the height is there, and then the starting point is here. So one point can move using these stairs, and then another person can move using stairs which are like this to reach the same point. So all the work that you have done is the same because you've covered the same height. So at this point, work done against gravity doesn't depend on the distance that you've covered, but how high you have gone. And so because of this, that means no displacement means no work done. Imagine you have got a very big load which you are pushing. You are pushing against as yourself. That's a very big load. So as long as this load doesn't move, you are not doing any work. What you are doing is wasting time. So you are not doing any work. So that is what we need to get to understand when we are talking about work. Alright, having understood work, let's look at power then. Just as we've understood work, we need to get to understand what is power. So what is this called power? So power is simply the rate at which you are doing work. How fast or how slow are you doing work? So this is the rate of doing work. And whenever we talk of rate, we should be able to think of time. So we are saying power is work over time. So someone who is much stronger is going to finish the same piece of work in a small period of time than someone who is weaker. So that means the one who has finished the work in a smaller period of time is much stronger, has got much power than the one who has taken more time to finish the same piece of work. So that is what we need to get to understand. Now notice that work is given by force times distance and then over time. Now consider distance and also time. So I can also write this as force, and then I can put d over t alone inside. Now remember, this d is a change in distance. When you've been given an object which is at position A and then it goes to position B, there is this change in distance here, d, which we can also say s as displacement. So distance over time gives us what we call velocity. Velocity is distance over time. So whenever you divide distance by the time, that gives you velocity. And so that means that power is also force multiplied by velocity. So this velocity is in the same direction as the applied force. Okay. So if something is moving with a velocity v in the forward, then it should be in the same direction as the applied force. You're applying a certain force F, and then something is moving forward. So we can also use that formula to find power. I didn't derive on work. On work, since we said work is given by force times distance, and we know that force is given in newtons, and then distance is in meters. So work is given as Newton meter, but 1 Newton meter is equal to 1 joule. And so work is given in joules, okay, as the SI unit. Same here, when we are talking about power, we are saying power is work over time. And we know that work is in joules, and then time is in seconds. So this gives us joule per second. So joule per second is a unit for power, but 1 joule per second is the same as 1 watt. So therefore, the unit for power is in watts. Notice that we can also find that power is in we are saying it is force multiplied by velocity. Force is in newtons, velocity is in meters per seconds. So we can also find it like that. We should never be surprised when you see that you find it in that manner. That is also power, newton meter per second. We also should be able to derive all these units of power. Of course, we know that power is given by work over time, and you know that work is given by mass times gravity times height, okay, mgh over time. But we know that mass is given as in kgs. This g is acceleration, which is in meters per second squared, and then the height is also in meters. Okay, sorry, I've put per there. Height is in meters, and then time down there is in seconds. So notice that we have got this meter and this meter which can multiply. So we're going to have kg meter squared per second squared, and then divided by second. So we can also say this is the same as kg meter squared. This per, we can also write it as divided by second squared, and then this is over, which we can say we can write this as divided by s. So it can give us kg meter squared over second squared times 1 over second, which is going to give us kg meter squared over second to the power 3. And this can be written as kg meter squared per second cubed. Or in some cases you can see it written as kg meter squared second to the power negative 3. It is all the same. So this is power. That's the unit for power. So all this which we can see is what is equal to a watt, a unit of power. Kg meter squared second to the power negative 3 is the same as a watt. Alright. Now, at times we are going to see something called a horsepower. Horsepower, and the symbol is HP. So horsepower is another unit of power. So this is a unit of power. So this is a unit of power. Just as power is measured in watts, it can also be measured in horsepower. So horsepower, this unit is mostly used for motors, engines, and such things, the horsepower. So 1 horsepower is given by 746 watts. So that is the conversion factor. That means if they've given us something in horsepowers, we are able to quickly convert to watts. Or if they've given us in watts, they want us to calculate in horsepowers, we can easily do that. Okay. Alright, let's consider another case now. So after understanding what power is, let me just give a very simple example how to convert between horsepower and also watts. Let's assume we have got an electric motor which exerts a force of 400 newtons on a cable. Okay, so we have got a cable here, and then you've got a motor this side. And then we are saying this motor is exerting a force on this cable of 400 newtons. And then it's going to pull something. Let's say this cable is attached to something, and then it's going to pull it for a distance, a certain distance. Let's say, let me say it is pulling it. So that is a force that is applied by the motor. So the motor is applying a certain force of 400 newtons, and that force is pulling the cable which is carrying a certain load and pulls it for a certain distance of 30 meters. Now I want to find the power supplied by the motor. You know that power is given by work divided by time, and work is given by force times displacement. The force is 400 newtons. The displacement is 30 meters. Okay, and then let's say we want to calculate the power supplied in 1 minute. So in 1 minute, we need to convert this to seconds, and we know that in 1 minute there are 60 seconds, so we're going to use 60 seconds. So that will give us 400 times 30 divided by 60, which will give us 200. We have got a newton here, we've got a meter there, and then per, because the second is down, that's why we've put per. We already said that newton meter per second is the same as a watt, so this is 200 watts. Now if we want the power given in horsepowers, we are going to say these 200 watts, we are going to multiply, because we have got a watt on top, we are going to take a watt down, we want a horsepower on top, and we know that 1 horsepower gives us 746 watts. So that is going to give us 200 divided by 746, which is going to give us 0.268 horsepower. So this is the power supplied by the motor in 1 minute. Alright. Away from power, since we've gotten to understand it, let's look at energy. And same as we've done with work and power, we need to know what energy is. So energy is something that gives the capacity, is a property that gives the capacity to do work. So that is the ability to do work. That is what we call as energy. A property that is going to give you the capacity to do work is what we call energy. Alright. Now we've got different forms of energy. Maybe the first thing that we want to look at, before I even look at the different forms of energy, when you are talking about energy, that without energy there is no work done. So work is equal to the amount of energy that is added on an object. So the amount of work that you've done is going to be equal to the amount of energy you've added to that object on which you are doing work. Alright, so having understood that, let's look at kinetic energy, which we can just abbreviate as KE. So kinetic energy, for us to understand this, we need to consider the work done to give something motion. So if you've got something that is not in motion, when it starts moving, so kinetic energy is simply the energy that makes motion possible, or the energy in motion. That is what we call as kinetic energy. Alright. So let's suppose we have got a mass that is at rest. Let's say a mass m, which is at rest. So we are saying kinetic energy is simply the energy that gives something motion, or the energy in motion. So let's consider an object of mass m, and it is at rest here, and then you apply a certain force F to this object. It starts to move, and then it moves, it covers a certain distance s, it reaches a certain point here. Okay, notice that the force is in the same direction of the displacement. So the object has moved from the point A to the point B. So for it to move, that means going in that direction. That's the direction of the displacement. And so even the force, according to Newton's second law of motion, force is given by mass times acceleration. And we know that work, because we already talked about work, work is given by, okay, we said work is given by applied force times displacement, and then cos the angle theta. Now here the angle theta is going to be 0. Okay, the angle theta is 0 here, and so cos 0 is going to give us a 1. So work will just remain as force times distance. So if we have got an applied force, notice that force is the same as mass times acceleration. So the work is going to be given by mass. Where there is force, we put mass, acceleration, and then you've got s. Okay, so that will be the formula for work. This applies when acceleration is constant. So when the acceleration is not changing, because this force which we applied was a constant force, and so the acceleration is also going to be constant. Alright, now we want to derive, we are talking about kinetic energy. We want to derive a certain equation which talks about kinetic energy. So we said we have got an object of mass m which covers a certain displacement s to reach a certain point, and then we applied a certain force F to this object. Remember, we said it is from rest. So when it starts moving at this point where it is going to be, it is no longer at rest, it's moving now. It has got a certain velocity at that point. So considering one of the equations of motion, v squared is equal to u squared plus 2as. So at this point, at the point of start where it is at rest, the initial velocity is 0. And then it is going to have a certain final velocity at that point. Let's call it point B. So we are saying the final velocity is v, and then the initial velocity, because starting from rest, is 0. And that will be equal to plus 2, okay, plus 2 times the acceleration. Remember, the acceleration is constant, it's not changing. And then because we're applying a constant force, that is why the acceleration is not changing. And then you have got what? S there. So all we've gotten is this. What we've just replaced is the u, which is 0. Alright. So from this, of course, we know from Newton's second law of motion that force is given by mass times acceleration. So that is going to give us acceleration being equal to the applied force divided by mass. All I have done is to divide by the mass on both sides to remain the acceleration. So in this equation where there is acceleration, I'm going to substitute what we have found. So that is going to give us v squared is equal to 2, where the acceleration we put F over m, and that times the s that side. Alright, so let's go on to simplify this. So this is going to give us v squared is equal to 2 times F times s divided by the mass. I've just multiplied the 2 and the force and the s which are on top. Alright, so in that manner which we've looked at, let's consider something now here. We have got this portion. Let me divide this so that I remain with only Fs alone. What I'm going to have is v squared is equal to 2 over mass and then Fs. So I haven't changed anything. What I've put is just put this like that. It's the same thing really. So at this point I can cross multiply. So I'm going to multiply this by that. So that is going to give us m v squared is equal to 2 and then Fs. So if I want to divide, let's divide by 2 so that we only remain with Fs. So I can bring it here. So that is going to give us, let me first take the second portion. Of course, this is going to cancel. So that is going to give us Fs is going to be equal to, instead of me writing just 2, let me say, okay, that's m v squared over 2. Which I can also write as Fs is equal to 1 over 2 and then mv squared in that manner. So at this point, let me just write from this. We are saying Fs is equal to 1 over 2 mv squared. Now notice that Fs, work, is given by Fs. And then what we have here, half mv squared, is kinetic energy. So what we are saying is work done. This which we can see here is the work done. Because we said work done is given by the applied force times the displacement. And then this, half mv squared, is the energy acquired, okay, by the mass to move from rest to do that kind of work. So we are saying the work done is equal to the energy acquired, and we looked at that. So work done is equal to energy acquired. So that is what we have come to find out. Very important equation to know. So what we are saying is kinetic energy is equal to, remember this portion is kinetic energy, is equal to half mv squared. And we are saying kinetic energy is equal to what? We have got this portion which is here. If this is kinetic energy, let me just try to clean up with what is happening. Okay. So we are saying this is work. And then this is kinetic energy. So what we are saying is work is equal to kinetic energy. Work done is equal to the kinetic energy. Alright. So that is it. That is the formula, one formula that we need to get to understand. Okay. Now let me give a certain example. So let's say we've been given an object. So we've got an object which is here, it starts from rest, and then there's an applied force. Let me just write it. Okay. So we apply a certain force on this object, a force F, which is equal to 20 newtons. And say we've applied that force at a certain angle of 30 degrees. And then what it does, it is moves a certain distance. It covers a certain distance. Let me give the distance as 5 meters. And then this object is 10 kg. Alright. So what we want to find is what will be the final velocity of this object. What will be the final velocity when it covers a certain distance of 5 meters? What will be the velocity here? Now, all we need to know is we've already derived that work is given by kinetic energy. Work is the same as kinetic energy. And you know that work is force times displacement. And kinetic energy is half mv squared. So the applied force, this force, remember we said force should be in the same direction as the displacement. So this force is going to be broken into the component that is going in the same direction as the displacement. Let me even use 40 here. Okay, so that means we are going to use the component of the force in the x direction, and that is given by 40 cos the angle which is 30. So this is a component which is in the same direction as the displacement, and then multiply by the displacement, which is our 5, and that should be equal to half. The mass of course is 10, but we don't know the velocity. So if we punch on our calculators 40 cos 30 and then multiplied by 5, that is about 173.2, and that will be equal to 5v squared. To remain with v squared, I'm going to divide both sides by 5. So that is going to give v squared being equal to 173.2 divided by 5. That is going to give 34.64. So to remain with v, we are going to take the square root on both sides. So that is going to give us a velocity of 5.88566, which we can simply say as 6 meters per second. So that is the final velocity when it covers a certain distance of 5 meters, if that is the case. Alright, so we have looked at kinetic energy as one form of energy. And it's not the only form of energy really that we need to get to understand. We also have potential energy. Let's abbreviate it just as PE. So the potential energy is the energy that is possessed by an object by virtue of its position. Energy possessed by object by virtue of its position. Alright, so that is what we call as the potential energy. So when an object is on a certain height here, it is not moving. It has got potential energy. By reason of its position, it has got potential energy. So when it starts dropping, the kinetic energy is going to be increasing. Remember here it wasn't moving, so the initial speed was 0. As it starts dropping, the kinetic energy is increasing as the potential energy is reducing. So as it hits the ground, every potential energy which was here has now been converted into kinetic energy at the bottom. Okay, so just the height, that's the original height at which this object is, gave this object the capacity to do work. So just at this point where an object is a certain h, a certain height h, this height has given this object the capacity to do work, so that when it drops, it is going to do work. Okay, and the amount of work done is equal to potential energy. Potential energy, which is given by mgh, is going to be equal to the amount of work which is done when an object drops from this point to the down. Alright, so getting to understand that, very important. Okay, so there is also what is called conservative and non-conservative forces. Now, what are these forces really? Now, conservative forces, these are forces which, when they do work, the work is going to reappear again in other forms. In other words, they conserve the work. These are conservative forces. They conserve the energy also. There is no energy losses. When you're talking about non-conservative forces, these are forces which are going to have some kind of loss in energy. So take for example, if you've been given an object which is at point A and then it goes to point B. So let's say you've got two paths. It is going to point B, it is coming from point A. You have got the first path, which is path 1, and then you've got a second path, let's say path 2. So notice that when this thing goes in this path, path 1, work done from point A to point B is going to be greater. Okay, so remember Fs is the work done. Work done is given by force multiplied by the displacement. And really displacement is simply the shortest distance between 2 points. Alright, so we are saying force 2 times displacement is going to be greater than force 1 times the displacement. So this is telling us that the work done in the second portion is going to be much more bigger than the work done in the first portion. The distance is longer here. When the distance is longer, that means even the work is going to be, a lot of work is going to be done. Alright, now consider this second path which I've shown here. When you want to go back in that manner, you might not get the same kind of work, because some energy is going to be lost, maybe as heat energy or as friction. So whenever there is friction, energy is lost. Because of that, friction is a non-conservative force. There is always some energy losses. Some other non-conservative forces that we can talk about is a push, a pull, even tension. So there is always some kind of energy losses. Alright, and these kind of forces, their work is path dependent. They depend on the path that you are taking. It doesn't matter. So if you consider conservative forces such as gravity, gravity doesn't depend on the path that you've taken. As I said earlier, whether you move from this point using the stairs or you start from this point to go up, it doesn't matter as long as you've reached the final position. So conservative forces are path independent, while non-conservative forces are path dependent. They depend on the path. Friction, push, pull, tension, they all depend on the path. So conservative forces include gravity, they include magnetic, and also elastic forces. So these don't depend on the path. These are conservative forces. And you see that kinetic energy is really not lost. If you, for example, if you lift an object from this point to the highest point, here it has got, let's say maybe it has got potential energy. When it reaches the up, it has got kinetic energy. When it drops back, the kinetic energy will be again converted into potential energy. But when we're talking about non-conservative forces, whenever you've done some work on it, whenever you've done work on an object, when you want to go back to the original position, the work is not going to be the same. Why? Because some energy is going to be lost as heat. Some energy is going to be lost in some different forms. So work is not always going to be the same when you're talking about conservative and non-conservative forces. Alright, in this video we end here. Thank you so much for watching. Stay blessed.